Problem number 3 says an electron is moving with a speed of 335 meters per second north along two adjacent current carrying wires as pictured below. So let's go ahead and just say this is the positive y direction. It's like we're looking at a map. Assuming that only the wires are affecting the electron. So that means don't worry about gravity, don't worry about anything else. It's just the wires that are talking to the electron. Now, of course, these two wires both have currents in the same direction. So the interaction between both of them would tell you that they would attract. Make sure we know that for the test. So two wires with currents in the same direction that are parallel to each other, they would attract. But we don't care about that. We're interested in how do each of these wires communicate to the space the electron is in. So what I'm going to do first is let's forget about the idea that the electron's there. Let's just pick some spots right there below where the electron is, and let's find the magnetic field at that spot, because the magnetic field there and the magnetic field there would be the same. Okay, so we'll do that. So what I'm going to do is this wire, if you take a look, this wire is communicating to that spot through that distance, and then the second wire is communicating through that distance. All right, and so the first wire, I'm going to go ahead and call this I1, and then this I2, so this is wire number 1 and wire number 2. So I'm going to find the magnetic field from this wire just at that spot. So how do I go finding the magnitude of the magnetic field at that spot? So B1 would equal mu naught I1 all over 2 pi R1. And the subscripts are there just to help me out, just to make sure that I'm finding the magnetic field due to wire 1. I need current through wire 1 and the distance to the spot. So mu naught, of course, is 4 pi times 10 to the negative 7th Teslas times meter over amp. That's just a given quantity. The current that it's currently having, no pun intended, is 4.5 amps. And then I'm going to divide that by 2 pi. And then R, take a look, it's 25 centimeters the other wire, but then an additional 0.15 meters. So the total distance is 0.4 meters. And if I punch that into my calculator, I should get 2.25 times 10 to the negative 6. Let me write that down. 2.25 times 10 to the negative 6 Teslas. And so that is the magnetic field due to wire 1 at that spot. Okay? Now, this gives me the size of it. How do I determine the direction? Well, current is going up, so my thumb would point up. There's my thumb. And then as I wrap my fingers around it, they'll wrap like this. That's terrible, but they'll wrap like that around the wire. And so when I'm on this side of the wire, my fingers would point in, and then they'd go behind and would point out at me. So at this spot, B1 points in. Okay? So it has this magnitude, but it points in. So I'll go ahead and write in. Okay, so that's what it's doing. Now we need to find the magnitude of the magnetic field due to wire 2. So that's mu naught I2 all over 2 pi R2. Notice I'm writing the formula again. So that's 4 pi times 10 to the negative 7th Tesla time meter over amp. The current in this particular case, I think, was 3.7 amps. Let's just double check. So 3.7 amps is correct. And then I'm going to divide that by 2 pi times the distance now is only 0.15 meters. And so when I do that, and I punch it in my calculator, I should get 4.93 times 10 to the negative 6 Teslas. That's B2. And then what I'll do is B2 is at that spot. Once again, the current's still going up, so I would wrap my fingers around the exact same way, so that would also be in. So B2 is also in, and so let me write that down. So this is 4.93 times 10 to the negative 6 Teslas, and that is also in. And since both of them are pointing in at the same spot, like at that location, so we could arbitrarily pick that spot right there. Since they're both pointing in, when I want to add vectors, since their directions are the same, remember when vectors point in the same direction, I simply just add them. So if I want to find B total, the total magnetic field, it would technically be B1 plus B2, and since they same the direction, it's simply 2.25 times 10 to the negative 6 Teslas plus 4.93 times 10 to the negative 6 Teslas. And so when we add those together, we should get 7.18 times 10 to the negative 6 Tesla. So that's the entire magnetic field at that location. All right, so what we first did was we determined the magnetic field at that location. Now it says an electron. Now let's keep that in mind. An electron is negative, so let's keep that in mind. Negative means opposite. And it's moving the speed of 335 meters per second north, which we call the positive y direction. So I know my velocity is 335 meters per second. We know that it's an electron. An electron has a certain charge. And so what I'm trying to do is I want to determine the acceleration. Now, how do I find the acceleration? Well, I can find acceleration by saying, hey, the net force equals MA, the only thing producing the net force is the magnetic force, or magnetic force, the field, which is producing a force, because it says assuming only the wires are affecting the electron, that's equal to MA. So once I find FB, I can divide both sides by the mass of the electron to get the acceleration. So now what I'm going to do is I know that the magnetic force, F sub B, is equal to QVB sine theta. All right, and so remember Q absolute value, that's fine, because remember this only gives me my magnitude right there. That's just magnitude. All right, and so QVB sine theta, we know it's an electron. The electron has a charge of 1.6, technically negative 1.6, but it's absolute value. So 1.6 times 10 to the negative 19th coulombs. My velocity, which was given as 335 meters per second, so write that 335 meters per second. My B field, which I just found to be 7.18 times 10 to the negative 6 Teslas. And then sine of the angle. Now remember, the angle is between V and B. So if I take a look, V is straight up in the positive Y, but because the B field is in, that's technically the negative Z, that's like into the page, that's 90 degrees. And so that's sine of 90 degrees, which we all know is going to be 1. So if I multiply all of that together, I'm going to get 3.85 times 10 to the negative 22nd newtons, and that is the magnetic force. And then, like I said above, the net force on it is equal to MA, and so the only thing producing the magnetic, or the net force is FB, and that is equal to MA. And so if I want to find the acceleration, that is the magnetic force all over the mass of the electron, because that's the thing that's in the electric field. And so it feels that force because it's in the electric field, or excuse me, magnetic field, not electric field, the magnetic field. And, And so what I'm going to do is FB is then 3.85, so 3.85 times 10 to the negative 22nd newtons, divided by the mass of an electron, which is 9.11 times 10 to the negative 31st kilograms. That's my acceleration. And so I get a value of 4.22 times 10 to the 8th meters per second. And so that's my acceleration. Now, here's where a lot of you guys would stop. Acceleration is a vector, which means that we need to also include a direction. So how do I determine the direction of the acceleration? Well, the cool thing is that the acceleration's direction and the net force's direction are always in the same direction. So A and FB are in the same direction. So remember, how do I find the direction of the force? I use the right hand rule. That's how I find the direction. So I have that. So if I take a look, let's go back up here. I'm going to redraw this picture, relook at it. So we know that the field is in and the velocity is up. So I want everybody to do this. I know this is crazy, but you're in front of your computer screen. You're going to do this with me in front of your computer screen. You're going to take your thumb and you're going to point in the direction of the velocity. So I'm going to take my thumb and I'm going to point it that way. Then I'm going to drive my fingers into the board. Well, if you do that with your right hand, you'll notice that your palm faces the two wires. Okay? So the right hand rule, thumb is up, fingers are in, my palm, which would cause the force, drives towards the wires. However, it's an electron. Electrons are negative. Electrons mean opposite. So my right hand rule, my palm is facing to the left, but because it's a negative, I know that the direction will be to the right. And so it's going to accelerate at that current state that it's in when it hits this magnetic field, moving in the positive y direction with that particular speed and that charge. It's going to feel an acceleration of 4.22 times 10 to the 8th meters per second. That should be squared because it's acceleration, so make sure you correct that. And it's going to accelerate to the right. So make sure this is a good problem. I like this one. Good problem. All right.